This video is over lesson 71, percent change of dimensions, and it is for my pre-algebra classes. So students, you may want to take a moment and pause to get down the information that I've already got written down, as well as you're going to probably want the handout that comes with this lesson. All right, so let's take a look. So today is about percent change of dimensions. So when we talk about dimensions, we're talking about one-dimensional dimensions, two-dimensional dimensions, three-dimensional dimensions. So real quick before I get into explaining and looking at our charts here, which are really just ratio boxes, let's take a moment and talk about one-dimensional measurements. So when we talk about a one-dimensional measurement, that is something that you could take a ruler to, typically, or somehow measure with a ruler. So when we think one-dimensional, we think about things like length, width. I'm going to write that a little better. Height, length, width, and height. Each of those is a one-dimensional measurement. If we think about specifically just polygons in general, side lengths. For that matter, think about right triangles, the hypotenuse, and the legs of the right triangle. Those would all be one-dimensional measurements as well. So if we take the sides of a figure and, well, of course, add them all together, you get a perimeter. Perimeter is a one-dimensional measurement. Now, you couldn't just take a ruler and just, with one measurement to actually measure perimeter, but imagine taking a piece of string and putting it along the edge of a figure. When you're all done, you could take that string and lay it out straight and take a ruler to that. So perimeter is a one-dimensional measurement. Speaking of perimeter, another perimeter is circumference. So also borrowing from that string idea, if you put a string around a circle and then lay the string out straight and measure it, you can find the circumference of a circle with a ruler. And since we're talking about a circle, for that matter, diameter and radius would also be one-dimensional measurements. I'm going to put a line here. Now let's talk about two-dimensional measurements. Well, your two-dimensional measurement, whereas the key idea here is length. Okay, the key idea of two-dimensional measurements is area. When you have a two-dimensional measurement, now you've got an area. Of course, if we're talking about something that's three-dimensional, it would have a surface area. And for that matter, we could also talk about its lateral surface area. Those would all be two-dimensional measurements. So whereas this is primarily measuring lengths, this is measuring areas, or we could say that it measures surfaces. An area is just how much of a surface we have. So that's all two-dimensional there. And then if we come over here to three-dimensional, we're talking about volume. There's not really too much more to say about that. So when it comes to volume, whereas there's a bunch of different lengths that we can talk about, there are different surfaces that we can measure. If it's just two-dimensional, we just find its area. That's the measure of the surface. If it's three-dimensional, we've got different surfaces along the figure that we can measure the areas of. Like, do we do the whole thing, or do we just do the lateral surfaces? When it comes to volume, since we live in a three-dimensional world, volume is pretty much volume. And volume, remember, measures space. So how much space something takes up. So this is primarily about lengths. This is about surfaces. This is about how much space something is taking up. So with that being said, let's go up and take a look at our ratio boxes now. So for this concept, we're actually going to have 3 different ratio boxes. And we're always going to need this first one, and depending on the problem, we'll include whichever one of these others that we need. So this all starts in one dimensional where things are nice and simple. We basically have a percent of change box, but instead of making this a percent, we're going to change it back to the word ratio. Because what I want to do with my percentages, just to make this really, really simple for you, is I'm going to change all my percentages either into a fraction or a decimal. And as I've said here, percent is a decimal. Decimal is going to be the most common. I will let you know that you could sometimes actually use a fraction here as well, but decimal is going to be most common. So since in a percent of change box, this original percent is always 100%, we change that to a decimal, which really is just the whole number 1. Down here we have our change, which is either an increase plus or a decrease minus. And then the new is just the one we started with, that 100%, plus or minus whatever this change was. Now remember though, this has to be as a decimal. It has to be as a decimal or a fraction sometimes. So when you write this in, make sure that you've converted it. Because from here, we're now going to move up to 2 dimensions. So if this is what's going on in 1 dimension, that we're going from 100% to x, or 1 plus or minus x, changed into a percent. So 100% into 1 plus or minus x changed into a percent. Then what will be happening in the 2-dimensional numbers here is we're actually going to borrow this right here, this 1 plus or minus x. However, since this is 2-dimensional, this is going to end up getting squared. And then when we move to 3 dimensions, we're going to do the same thing. We're going to take whatever this number is, but this time, since it's 3-dimensional, we're going to cube it. So if you want to know how much the 2-dimensional measurements have changed, we're going to have to take this new amount and subtract the original to figure out what that is. So this means you're going to take whatever this number is right here. Just for simplicity's sake, let's go ahead and call this right here. So we got that x. We're going to call this y. So then this here would be y minus 1. So whatever this result is, minus this 1. Now, if this ends up being a negative, we're just going to make this a minus. So we'll put the sign out here next to change. So if that's negative, we'll put the negative sign there. If this is positive, we'll put a plus sign here. Likewise over here, let's call this result here, this 1 plus or minus x cubed. We'll call this z. So then to find its change for 3-dimensional measurements, it will be z minus 1. And again, if this is negative, we won't put the negative here, we'll actually put it out there. Now, ladies and gentlemen, that's the key there. There's no way around what we've just talked about. So we are going to have to start, and we'll look at some examples here in just a second. We will have to start with the 1-dimensional ratio box. We will take this result, and you square it to find this. You cube that result to find this. Whatever this guy is, subtract 1, and you've got its change. Whatever this guy is, subtract 1, and you've got its change. So underneath here, let's take a look at our examples now. So just to remind ourselves where we're finding these, let's go ahead and write C, lesson 71, ICE sheet for examples. Oops. EXA examples. So example 1. And I'll bring my sheet over here and let's look at this together. So first of all, ICE, ICE stands for in-class exercises. And I have actually borrowed this from one of my college professors, thank you, Dr. DeLong, who would regularly give us handouts like this as we'd work through our Calculus 3 problems, actually. And then I had him again for differential equations, and we did the same thing. So I'm borrowing this from him. So thank you, Dr. DeLong. So ICE. So number 1, the area of one figure is 30 square inches. It is increased in size by 50%. What is the area of the new figure? What is the change of percent in area? So here we go. We're going to slide my paper up there. So for example 1, we are going to start with our one-dimensional box. Now we weren't given any actual numbers for the one-dimensional measurements, so I'm actually going to make a simplified box here. And instead of doing the whole ratio box, I'm just going to do the ratio column. That's all I really need to know in order to find the change in my two-dimensional measurements. So I'm going to do that. Now you'll notice I didn't leave a lot of room over here, because what I'm actually going to do to save some writing is I'm going to write the labels for these rows over here on the right this time. And so let's go ahead and fill out our box now. So we always start with 1. Remember that 1 really is 100%. So the original is 100% of itself. That's all we're saying. The problem said that this was increased in size, so an increase is going to be a positive change. Increased in size by 50%. So we have to change 50% into a decimal here. So that should be pretty easy. You all should have that memorized. 50% is 0.5. So 1 plus 0.5 is 1.5. Or if we change this back into a percentage, 1.5 would be 150%. So the new figure will be 150% of the original figure. But I don't want to know about the one-dimensional measurements. I want to know about its area. So remember that area is a two-dimensional measurement. So what I'm going to do here now is I'm going to borrow these 3 labels here for my two-dimensional ratio box. That way we don't have to write all that twice. So this will be two-dimensional. This will be a new group of ratios, and we'll actually have some actual information to put in. Remember, this is always 1. The original is always 100% of itself. Always 1. That will not change. The problem tells us that the area of one figure is 30 square inches. So I know that the original was actually 30 square inches there. So I'm going to put that 30 in. We don't know how much it's changed, and we don't know what the new area is. But we can figure out these two using this information here. So I'm going to take this number here, and since it's two-dimensional, I'll take 1.5 and square it. And that's what's going to go in here. Since two-dimensional, we're just going to square it. So if you grab your calculators, or if you have it memorized what 15 squared is, that could help. And if you do that, you'll discover it is 2.25. Now, if we change that into a percentage, then what we see here is if the new is 150% of the original, then the new figure's area will actually be 225% of the original figure's area. So what was the change here in percentage? Well, remember, it's going to be our result here minus 1. So it's going to be this 2.25 minus this 1. So 2.25 minus that 1, 1.25. Or if you want to look at it another way, 1 plus what is 2.25? That would be another way to look at it. So with that, we can go ahead and make a proportion to solve for what is the area of the new figure. So I just want the area of the new figure, that's y. So my proportion is going to be the original row, because I know both 1 and 30. But then I'm also going to use the new row, because that's what I want to know. So 2.25, and then over y. And we're ready to go ahead and multiply. Now the nice thing about this here, y times 1 is just y. So now we need to figure out what is 2.25 times 30. Well, 2.25 times 30, if we throw that in our calculator or work it out, is 67.5. Remember, the units here were square inches. So the new figure that is 50% larger will actually have more than 50% of the area. Its area will actually be more than double the original figure's area at 67.5 square inches. Last of all, we're asked what was the change in the percent of area. This is the change. So all I'm going to do is just show a little bit of work here. We're going to write that 1.25 down. We're going to multiply it by 100% just to show how we do that. And so it is a 125% increase. We got to give a nice label here. Increase in area. So a 50% increase in size, so each of the sides of the figure are made 50% bigger, will actually increase the area. There'll be an extra 125% of what there was before. So you'll still have 100% and then another 125%. Let's take a look at example 2 now. The volume of a cube is 4 cubic centimeters. It is increased in size by 10%. What is the new volume? What is the percent change in volume? Okay, so this time we're going to do a volume problem. So example 2, remember, ladies and gentlemen, it always starts with our one-dimensional. Now, since we were not actually given any lengths, widths, heights, or anything else like that, I'm just going to do, oops, and I made a mistake. My apologies. I forgot to label my column. We're just going to do the ratio column of the one-dimensional box. That's all we need. Our labels are going to go over here so that we can share them. And now let's go ahead and fill it in. So the original, remember, is always 100%. Change into a decimal is 1. We're told that it is increased in size, so that's going to be a plus. Increased in size by 10%. Change that to a decimal, 0.1. So the new figure has 110% of the original. Now we're going to come over Let me give myself just a little bit more room there. That's better. So ratio, actual, and remember this, now we're going to look at the 3D stuff. So volume is three-dimensional. Well, it's always 100%, and we're told that its original volume is 4 cubic centimeters. I don't know the change, and I don't know the new. Like we did before, we're going to take this number here, but since we are working in three dimensionals, we're going to cube this to find that number there. So 1.1 times 1.1 times 1.1 turns out to be 1.331. So if we're to change that into a percentage, that would be 133.1%. So the new figure will have a volume that is 133.1% of the original figure's volume. All right, and then to find the change, well, if this was an increase, then the volume over here will also increase, so then plus for both of them. So 1 plus what is 1.331, or 1.331 minus 1 is what? Either way you want to look at it. So that should be fairly simple. 0.331. So now I want to know the new figure's volume. So again, we're looking for the new, and we know the original. So this will be 1 over 1.331 equals 4 over y. And if we cross multiply, 1 times y is nice and easy. That's y. Makes it easy to solve. And then I just got to do 1.331 times 4. And if we go ahead and plug that in, we get 5.324. Remember, the units were cubic centimeters. So not as drastic of a change as we saw here in example 1, but you've got to remember that example 1 had a change of 50%, whereas this is just a change of 10%. So last thing, we're asked to find what is the percent change in volume. So that's going to be this right here. That's my change for volume. So 0.331. To change that to a percentage, we just multiply it by 100%, and that'll be 33.1%. Oh, I'm sorry. Little mistake. We got to have more of a label there. 33.1% what? Well, it's a percent increase, since that's a plus, percent increase in volume. I knew I was forgetting something. I'm glad I caught that. 33.1% increase in volume. All right, and let's go ahead, and I'm pretty much at the bottom of my page. I imagine you are too. So let's go ahead and throw example 3 on the back of our paper. So example 3, and let's take a look at it. The surface area of a solid is 80 square feet. It is decreased in size by 60%. What is the new solid's surface area? What is the percent of change in surface area? So here we go. We always start with our one-dimensional stuff. I'm going to label the column this time, and then I'll make my 3 rows. This is the original. Here we find the change, and then finally the new. So the original percent is always 1. This time it is a decrease so a minus there, a decrease by 60%. So 60% as a decimal, remember I always change it to a decimal, is 0.6. So therefore 1 minus 0.6 would be 0.4. Now I'm going to come over here and make my next box. And this time it's asking about the surface area. So remember, surface area is a two-dimensional measurement. So we got a two-dimensional measurement this time. Well, original is always 100%, which as a decimal is 1. This time we're told that the actual surface area of the original is 80 square feet. So we start with 80 here. And now we're ready to figure out the rest. So if this is 0.4, remember we're going to take this result here, 0.4, and since it's two-dimensional, we're going to square it. And that's what's going to go right here. So 0.4, 4 times 4 is 16, but one decimal place and then another decimal place will make two decimal places for that 16. So 0.16. So if we change this to a percentage, if you do a 60% decrease, that means that the new figure will be only 40% the size of the original, but that the area will only be 16% of the original figure's area. So it has a more drastic change in the area. So now again, there are two different ways that you can think about this. We could just take our 0.16 and subtract the 1 to figure out what this is. We already know that's going to be negative. That's why there's a minus out here. Or you could think of this as 1 minus what is 0.16. Either way works. And either way, we should get the result 0.84. Now, I don't know this and I don't know that. And now we are ready to go ahead and find our answers. So what is the new solid surface area? So again, we want this new surface area. So that's going to be 1 over my 0.16, 1 over my 0.16 equals my 80 over my y. Y times 1 is y, and 0.16 times 80 is 12.8. Now, if we go ahead and look back at the problem, we'll find that our units are square feet. So the new figure will only have 12.8 square feet for its surface area. That's a big change. That's a big drop. So finally, what is the percent of change in the surface area? So here's my percent of change. So I'm going to take my 0.84 and actually change that decimal back into a percent, multiply it by 100%, and that'll make it 84%. But this is a decrease. 84% decrease in surface area. So a 60% decrease in size will actually have an 84% decrease in area. So one of the things that we notice throughout this is that as you change the size of a figure, its area will be affected more and its volume will be affected even more. And that, ladies and gentlemen, is the end of our lesson.